Question is, which is brighter, 60 watt or 100 watt? I'm about to find out. All right, here is a 40-watt light bulb. I would suggest not looking straight away at this, but that's my suggestion. Here's 40. Here's a 60. 100-watt light bulb. And a 200-watt light bulb. Okay. Okay, so so the important question is why? Why is a 100-watt light bulb brighter? Okay, so power is the rate at which energy is being converted. Electric potential energies can be converted to some other type of energy. Okay, there's more electric potential energy being converted per second with the higher wattage light bulb being converted to heat and light than a lower wattage light bulb. Does that make sense? Okay, that's how quickly energy is being converted. There's more energy per second being converted to higher wattage light bulbs. Okay. So, last semester we talked about power is equal to the rate at which work is done. Last night you're like, it's equal to the rate at which electric potential energy is being converted to another type. That was not that too big of a jump. Work and energy, both are measured in what? Good, joules. Okay. So joules per second, that is what a watt is. Okay. But then I introduced this other equation. Power is equal to current times voltage. And I don't know if any of you thought, like, that doesn't make sense. Okay, we'll just go with it, sure. But I want to show you how these two, the purple and the blue, go together. Okay. What's the unit for current? Good, amps. What's the unit for voltage? Volts. Amps times volt. Not helpful. Amps comes from coulombs per second. And volts comes from joules per coulomb. Hey, wait a minute. The coulombs cancel out. Crazy. That's so cool. All right. So conceptually, here's why that makes sense. So let's say you have a circuit, and let's say this wire. I'm walking along. I'm an electron. Here's where the light bulb is. Okay. Over here, the electrons have a lot of energy per electron. They're packed together. They're closely packed together. There's a lot of potential energy there. As they come and they hit the light bulb, they give that energy, some of that energy, a lot of that energy to the light bulb, and that's converted to heat and light. Okay. So what electric potential is, what volt is how much energy each electron is giving, is contributing to the light bulb. current talks about how many electrons are coming by giving that energy per second. Just like, here you go, here you go, here you go. So if you know how much energy is being given per electron and you know how many electrons are going by every second, then you are able to figure out how much energy is being contributed per second. Good with that? Some of you are like, it's okay, Mr. Smiley. I'll just do the equation. You'll be all right with it. Okay. Thumbs up when you have a guess. Okay. I want to get rid of voltage. Okay. So voltage is equal to current times resistance. So what I'm going to do is I'm going to substitute this in for voltage. So power is equal to current times resistance. See how I did that? Correct answer is B. Okay. I will give you these two equations. I will not give you this. It's kind of a shortcut, handy thing to have in your back pocket. Okay. This is a similar question. It's just, how do you do it in terms of just voltage and not current? Tell your neighbor. So we know that current is equal to voltage over resistance. Correct answer is A. Good with that? Thumbs up when you have an answer. Talk to your neighbor. Yeah. Correct answer is C. Next question. Okay. Which causes a greater increase? Okay, which will cause a greater increase. Thumbs up when you have a guess. Talk to your neighbor. Correct answer is B. You got it squared. Good? Next question. This? Oh, dissipated? I thought I just said, what a disappointment. Dissipate is just the verb we use for power. Uses, gives off.
In Spanish, like if honestly, it just Hey, I'm not saying
All right, what do you think? Okay, I will show you the long way, the tried and true, and then the shortcut. For this, which of those three measurements are staying the same? The voltage. Why? It's determined by the battery. Whatever the power supply is, that determines the motivation. That determines the pressure. If you're not changing the battery, you're not going to change the voltage. Okay, so the voltage stays the same. Our resistance is increasing. Therefore, what happens is a current, if voltage stays the same and resistance increases, decreases. That makes sense mathematically? Voltage, again, stays the same. Battery didn't change. Current, we said, goes down. Therefore, power does what? Also goes down. Correct answer is B. Good with that? Here's the shortcut. You got these two expressions. I want to use the expression where one thing is held constant and all three aren't changing. So I'm going to focus on this one. Okay. The voltage is constant. Here, this changes, this changes, this changes. That's kind of hard. It's a little fuzzy. This, if one of those is constant, you know that how one affects the other. So as resistance increases, what happens to power? Decreases. JP. Yeah. I mean, if you'd use that one if current stays the same. Does that make sense? I mean, did you know where these came from? It just came from combining these two. So you can come to the same answer without any of these. It's just the faster way to do it. Okay. Thumbs up when you have a guess. Talk to your neighbor.
What is dissipating?
Gives off. It's the verb we use for power.
Okay. Okay. I don't think that changes this.
It doesn't.
Okay.
Dissipated is just the verb we use for power. It means gives off. How quick, like energy, that the rate at which energy is being changed from electric potential energy to something else. All right, what do you say? Here we go. So, what's staying the same? We got a 6-volt battery. That's not changing. So, as we get brighter, power goes up. Therefore, current must what? If voltage is staying the same, must go up as well. So the brighter, power is increasing. Okay. Voltage is staying the same. As current goes up, what has to happen to resistance? Has to go down. So the brighter one has the least resistance, the lesser resistance. We're asked to find which one has the larger resistance. So therefore, it's the dimmer one. B, bulb 2, is the right answer. Good with that? Okay. Calculating your electric bill. This is super practical. Oh, sorry. This type of question, it will be on your test and will be on your final exam. Mhm. I'm gonna show you how to do it. I'm trying to like emphasize how, emphasize, struggle today, emphasize like you're gonna have to do this. So the reason why I'm want you to do this is because I feel like this is super practical. You're gonna have to calculate or like pay your electric bill at some point in the near future. Okay, whether in college or post. Like, and to know what you're actually being charged for, I think is a really good thing to know.
Like, I'm just gonna call my dad.
Yeah. Oh, my mom.
So we're gonna assume that there's 30 days on average. Okay, so here we go. So power is equal to the energy, electric potential energy over time. So we got 60 watts. What do I need to convert my time to? Seconds. So we're going to assume there's 30 days just on average. That's a pretty good average. 30 days in a month. There are 24 hours in a day. And there are 60 minutes an hour and 60 seconds in a minute. And that's going to be a big number. That's a lot of seconds. It's actually, oh, I had that. Things like 5 million. I don't know. 30 times 24 times 2,592,000 seconds in a month. So the potential energy that we dissipated times 60, 1.555 times 10 to the 8th, which is 155 million joules. For one light bulb. That is an obnoxious number. Okay. You see how we need another unit, a different unit. Something is like, that's like saying, oh, there's 155 million inches to California. I'm like, great, thanks. Miles, that's more appropriate. Okay. So we need another unit. And so this is, the power companies have created this unit. It's kilowatt hours. Okay. This is the only time you're going to use this or do this, is not convert to seconds, but you're going to convert to hours. You're not going to have it in watts. You're going to have it in kilowatts. Okay. Only time you're going to do that. But this is the tip off. Like, this is the thing that's going to be like, oh yeah, because it's going to have kilowatt hours in the problem somewhere. Okay. So same equation. Tell your neighbor how you're going to convert this to kilowatts. Hey, here's a connection. Ready? What does that mean? $1,000. Okay. So we're going to divide by 1,000. 1, 2, 3 decimal points. Okay. And then we need to convert not to seconds, but to minutes. So I don't have to do the times 60 times 60. I just need to figure out how many hours are in the month. Does that make sense? So there's 720 hours. And we find this to be 43.2 kilowatt hours is the amount of energy, electric potential energy, that's being converted to heat and light. And that is a much more reasonable number than 155 million joules. Okay. Using that, we can figure out how much our bill is. So I've got 43.2 kilowatt hours times, I've got this rate, 9 cents per kilowatt hour, meaning 9 cents for every 1 kilowatt hour. And that ends up being $3.89. Okay? $3.89. Depends on what time of the year. $200, $300 per month. Okay. Yeah, if it's during the summertime, your air conditioning unit is like huge electrical drain. Like $100 a month.
Well, that's not a bad deal. It's way worth it.
Depends on how much you're making. Okay. All right, last question. Last question.
Did it do good or bad?
I hope on this do well.
Oh, this is the homework. I thought you were trying to test.
I know. I haven't. Yeah, I was soft on you guys last semester. Nope. No. We went too slow last semester.
That's so fun. I don't know why that's what why is that what you thought of? Pass grades were much higher last semester.
Okay, correct answer is energy. Okay, that's what you are. That's what kilowatt hours is energy. Unit of energy. That's what you're charged for. Power is the rate at which you consume that energy. You're being charged by energy. We are, except I'm going to go over the test.